Okay, so to go over some of the specifics. So the first section that we did was our exponential growth and decay. We created the equation from scratch, like kind of starting off with the differential equation, the dy by dx. You don't have to do that. Okay, so you'll have this y equals ce to the kt, and just know that equation, have it memorized, be able to sub stuff in so that you can use that equation. You will have two initial conditions or two pieces of information that will be given to you. So those two initial conditions, the first will allow you to solve for C. The second initial condition, once you also have the C, will allow you to solve for K. Make sure too, so I mentioned the first one says you should be solving for C. With these ones, C is the initial value. So if they tell you like the initial population is 60 million, that's C. Or if they tell you like the initial amount of, carbon, anything that they tell you the initial value is, with these problems, that's always just C, because if you plug in 0 for T, then Y is just equal to C. That's not true for Newton's law of cooling. Okay, so make sure you've got those separated out. Exponential growth and decay has nothing to do with temperature. It's just talking about some sort of population that is either growing or shrinking as time passes. So you should have no problem distinguishing between the cooling problems and the exponential growth and decay problems. The Newton's law of cooling problems will also mention a surroundings. Like they'll be like, oh, it was put into a freezer that's kept at 10 degrees, or it was in a room that's kept at 65 degrees, or whatever they mention. So if there are no surrounding temperatures mentioned, then it's probably exponential growth and decay. For the value of C, if they give you a starting point, assume that that is t equals 0 and work from there. Okay, it's like whatever your starting point is, assume that that is t equals 0. There was a population one that we did together in class that the first condition that was given to you was the year 1960. We just assumed that 1960 was 0, and then we went from there. If I had asked you about 1950, that would be -10. If I had asked you about 1975, that would be t equals 15. So always start with t equals 0, and then just move forward or backwards from there. K, store K. Please make sure you store K. You guys saw with that example that we did together, we were off by like 19 million people when we did not store the value of K. So please make sure you know how to do that. I would be happy to walk you through it before you guys leave today if you don't remember or never knew how to store K. So make sure you've got your graphing calculator with you for the test tomorrow. I think, oh no, I do want to mention one more. Need to check a page number. There was one problem that I want you to make sure that you're comfortable with. The one that said 15% remained, because I'll give you guys one of those where it's a percentage rather than an amount. So I want to give you the comparison so you guys can write the page number down. Okay, it's page 123. I want to show you which one I'm talking about. This is just a blank page, but so something like this. So it talks about carbon dating, blah, blah, blah. And it says a piece of ancient charcoal contains only 15% as much, and then it gives you a half-life. So you'll need to know how to do a problem like that as well. So write down that you need to know this. Example number 2 on page 123. So understanding, even if they don't give you an initial condition, they could still give you a percentage, and that's enough information to work from. So you'll have to do something like this, where either a half-life or a doubling time will be given to you, and then it'll say when is there this percentage left over? And you should be able to solve for T, even though you don't have an initial condition. They gave you percentages, and you should be able to work from there. So that was example number 2 on page 123. So make sure that you're comfortable with problems like that as well. So any additional questions on exponential growth or decay? Okay. Seconds, while we're talking about these types, let's talk Newton's law of cooling. So this is a very similar formula, except you have plus the temperature of the surroundings in there too. So these should be easy to recognize. You're taking an object from a cool environment and putting it into a warm environment, or you're taking an object from a warm environment and putting it into a cool environment. So it should, just by reading the phrasing, it should be easy to know whether it's one of these types of problems or one of these types of problems. The other thing I mentioned specifically, they will mention the temperature of a surroundings. Like, oh, it's put into a refrigerator that's kept at 38 degrees Fahrenheit, or it's put into an oven that's kept at 350 degrees Fahrenheit. So they will mention surroundings and what their temperatures are, and that will indicate to you that it's Newton's law of cooling. So you've got basically like the same stuff that you've got here. Like I could copy and paste this information just into this section. You'll have two initial conditions. It will tell you, like with the dead body problem, like at t=0, the temperature was this. 2 hours later, the temperature was this. So S is going to be directly handed to you, but with your initial conditions, you use your first initial condition to find C, use your second initial condition to find K. Remember with these ones though, the initial condition is not automatically the value of C, like it is with this type. So make sure you're actually setting it up and solving for C with these types. Same advice with this, your starting point is t=0. So like with the dead body problem, when we found the body, we considered that to be t=0. And then you just use a negative time for the time of death. Same thing, store K. So this, like almost all of this information that I could tell you from exponential growth and decay, just, copy and paste it into this section. Just make sure you know the slight difference between these formulas. Questions on Newton's law of cooling? Okay, and our differential equations was our third of 4 topics. So this is our 3-step process. We separate, we integrate both sides, and then we isolate y. So that was our rhyming way of saying that in this third step we're solving for y. So separate the variables. dy by dx does not allow you to choose which side you want the variables on. Like if you have dy by dx, it means the y stuff is going to be on the left, the x stuff is going to be on the right. It's like you never get to choose which side is which. When you are integrating, I give you 2 pieces of advice here. Make sure you have a plus c on the rights. And make sure you keep an eye out for u substitutions. So you should still know like all of the tips that we had from the previous test that you guys just got back. Any integration that popped up there, you should be able to do in this integrate step. So they're not always just necessarily going to be simple power rules or, e to the x or sine or cosine or something like that. Look for u substitutions, meaning you'll have something that looks like it's nested and then its derivative will be in there somewhere. So like maybe there's a sine that looks like a nested function, and then there's a cosine in there somewhere that would get swapped out as the du. 2 of them are going to have a solve for c. So these 2 steps are interchangeable. You can solve for c at any time that you want, just as long as you get the y by itself at the end. So there will be 3 of these. 2 of them will be particular solution. 2 newtons and 2 exponential growth and decay. So again, out of these 3, 2 of them you'll have to solve for C. 1 of them you'll just leave as a general solution because you won't have an initial condition. And our last topic, slope fields. So when you're creating them, you're really just taking each ordered pair and plugging it into the differential equation and then making these like tiny little line segments. So you're just plugging in your ordered pairs into dy by dx. So at every ordered pair, and I'm not going to give you like 20 points on the line. I think they're like 8 or 9 or something. So nothing too crazy. I'll get whether you know what you're doing or not with a handful of points. So each ordered pair, you plug it in. And I saw some of you guys doing like the little formula, like just plugging in X for the whole column. That's great. Gives you a nice little shortcut. So if you plug in like X equals -1, X equals 0, X equals 1, and create a little formula where you only have to then go and plug in the Y's, it's a shortcut. For the matching section, I'll give you my best advice here. So first thing you want to look for is if they come in either horizontal stripes or vertical stripes. That means they're one variable. So if they come in horizontal stripes, if they come in horizontal stripes, they are a single variable. Which variable? It's just in terms of y, if they come in horizontal stripes. Remember that y equals lines come as horizontal lines. If your slope field is in vertical stripes, that means